Hi, it's Mr. Anderson, and in this podcast, I'm going to talk about bioenergetics. Bioenergetics is basically how living systems make use of free energy. And so this plant right here is called Arabidopsis, and basically to the right of it is a diagram showing the metabolism of just the Krebs cycle in Arabidopsis. So basically, this is how it's converting acetyl-CoA into carbon dioxide and then making NAD and fat. And so this is incredibly complex. Each of the red dots represents an enzyme, and each of the lines represents chemicals moving between those enzymes. And so you can see that it's incredibly complex, but you need to know the basics of bioenergetics. And I could sum it down to this. Life requires free energy or available energy. In other words, right now as you think, your brain is cashing in ATP. And if you don't do that, then you will die. So the opposite of using free energy is death. And so basically there are two laws of thermodynamics. First law of thermodynamics you're probably familiar with. It's basically the law of conservation of energy. In other words, energy is converted from sun to wheat to plants to ATP to ADP using that energy in your brain. And so basically the total amount of energy in a closed system is going to be constant. In other words, we can neither create nor destroy energy at each step. We're simply converting it. All energy will eventually end up as a lowest form of energy, which is heat. People are usually not confused by that, but are sometimes confused by the second law of thermodynamics. And basically what that is that as we move through time with each chemical reaction, we're increasing the entropy or the randomness of the universe. In other words, with each chemical reaction from the sun to the ATP in your brain, we're losing order, or it's becoming disordered. Now, what seems to run counter that is the idea of evolution. The evolution seems to make things that are more and more complex over time. And some people point to this as a way that we're violating somehow the second law of thermodynamics, which would be true if evolution occurred over the whole universe. But remember, we're simply one part of the universe. And so we can increase order in one area by decreasing the order of the universe around it. So that's basically the second law of thermodynamics. Next, we come to the idea of Gibbs free energy. Some kids are confused by Gibbs free energy, so we're going to step through it kind of in a cartoon method for talking about Gibbs free energy. This equation is sometimes what confuses you. And so basically, the important thing to understand is what happens with a change in Gibbs free energy or change in free energy. And so we've got three terms that we're going to kind of keep track of. H stands for the total energy, T stands for temperature, and S stands for entropy. And so basically the first thing that you should think about is that free energy, a better way to think of that is available energy. And so what we're going to do is go through three spontaneous reactions. In other words, reactions that occur on their own. And we're going to look at these values of H, T, and S. So let's start with the first one. This is a ball at the top of a slide. Think about this. Does it have more energy at the top of the slide or at the bottom? And the right answer is going to be at the top of the slide. It's going to have more potential energy or energy available to do work. And so let's look at what happens to the H value. So the H value is going to go down in a spontaneous reaction. Let's go to the next example. Let's say that we have a number of molecules that are in a closed container, and think of these as gas. And so the gas molecules are moving around. And let's say I remove one of the walls inside this container. Well, since they're randomly moving around, they're going to spread out, covering that area. That's going to increase the entropy, or S is going up in this case. We're becoming more and more random. Let's say we remove the whole container. What's going to happen? Well, S is going to increase as well. So again, in a spontaneous reaction, the amount of entropy is going to increase. Now let's look at the last one. Let's say we have this bomb here. Is that spontaneously going to explode? No. But let's say we increase the temperature. What's going to happen then? Well, now we're going to have that spontaneous reaction. And so again, this is kind of cartoon look at Gibbs free energy, but let's just let's kind of summarize what we've learned. So in a spontaneous reaction, delta G is measured in this case. So delta H, T, and S. And so looking back to the first one, in this spontaneous reaction, what happened to delta G? In this case, the delta G actually went down. So delta G went down. So what should that do to the change in G? That should decrease it. Well, let's look at the next example with the molecules as we spread out. What happened to those? Those ones increased. What else can increase a spontaneous reaction? An increase in the temperature. And so thinking mathematically, if you increase these two values and we're subtracting it from the total energy, what's going to happen to our delta G? Our delta G is going to be negative. And so that's a lot of stuff, but here's the summary. Basically, if we ever have delta G, and delta, remember, change in free energy is less than 0, that's a spontaneous reaction. If delta G is ever positive, that's going to be spontaneous in the opposite direction, and so non-spontaneous. Lots of times we refer to this as an exergonic reaction and this as an endergonic reaction. And if delta G, or the change in free energy, is 0, that means we're at equilibrium. So we've talked a lot about what seems like physics, but we haven't talked about biology. And so let's get to biology. Let's say we have a molecule here of glucose in the presence of oxygen. Is that an exergonic or energy releasing, or endergonic, an energy taking reaction? Well, that's going to be an exergonic reaction. It's releasing energy as we move from glucose and oxygen to now carbon dioxide and water. If we look down here at the delta G value is going to be negative 686 kilocalories per mole. What does that mean? If you take a mole of glucose, you're going to release that much energy. And so it's giving off energy. So our change in G, or change in free energy, is negative. Where was that energy? The energy is actually in the hydrogen here, because the hydrogen has a lot of potential energy. And as it falls, watch the hydrogen, it all grabs onto oxygen. So we're losing that energy, and we can release that energy. Now let's look at an energy diagram. Well, basically that glucose and oxygen have a certain amount of free energy over here on the side, and when it's done, they're going to have less energy. And so if I were to draw the energy diagram, it's basically going to go up, and then it's going to go down. So this is what an exergonic, or energy releasing reaction looks like. Now, if you know anything about chemistry, you know what this is up here. This up here is called the energy of activation. In other words, you know that just sugar sitting on your table doesn't spontaneously break into water and carbon dioxide and giving off, fire. Basically, you have to put a little bit of energy into it to loosen those bonds, and then it's spontaneously going to break down. But if you look at that the net change from delta G here, G, or free energy here, to free energy here, you can see that there's a decrease in that. And so the delta G is going to be less than 0. That's in an exergonic reaction. If we look at the next one, this is photosynthesis, which even though chemically it's not the exact same steps, it's doing the opposite. We're going from carbon dioxide and water with the energy of light, and now we're making glucose. And so if you look down here at the delta G, now it's a positive value. And so that's an endergonic reaction. It requires energy. If we look at the energy reaction, or the diagram for that, basically we have less energy than we do at the end. And so what's happening? Well, we still have activation energy, but if we look at the delta G, it's going from a small value to a greater value, and now we have a delta G that's actually greater than 0. So this is an endergonic reaction. So in a plant, where does this energy come from? This energy comes from light, and so light is providing the energy to actually boost it to a higher free energy. Now, why are plants doing that? Remember, they're doing that so they can do cellular respiration and then release all that energy in the form of ATP. They're not making that sugar for us. They're making it so they can have a storable amount, glucose, and then they can break it down in doing cellular respiration and then produce energy in the form of ATP. Speaking of which, this is ATP. So this is adenosine triphosphate. This last phosphate, remember, can unattach. And so if we do that, what's happened to our delta G? It's negative. You can see that's a lot less than it was with cellular respiration, and that's because it's a smaller molecule. If we go back to ATP from ADP, that's going to be a positive delta G. If we break the phosphate, negative. If we form the phosphate, that's going to be positive. And so constantly inside my body, as I move my muscles, I'm breaking that ATP down to ADP to provide energy, and then I'm making it again through cellular respiration. And so what's important when we're talking about bioenergetics? Well, there are two big chemical processes that are super important. First one is photosynthesis. This occurs in the autotrophs, or the photoautotrophs. Basically what they're doing is taking the energy of light, and then they're using that to make glucose. And then secondly, they're taking that glucose through glycolysis, Krebs cycle, electron transport chain, and then releasing that in the form of ATP. In the next two podcasts, I'm going to talk specifically about photosynthesis and how that occurs, and then cellular respiration and how that occurs. But remember, the reactants of one are the products of the other, and vice versa. And so the delta G is going to be the same. negative in cellular respiration, positive in photosynthesis, and I hope that's helpful.